Alright, so I've started the recording. So we will continue with this mutability and imperative control flow, and we'll finish this today. So we're going to go through some best practices for using mutable state and side effects. Okay, so let's get started here. So we are going to show some patterns and anti-patterns relating to mutable state and side effects. Okay, that's what we're going to cover here. And there are some good practices and there are some bad practices, so we will go through each one of those. So here is a good example for function encapsulated mutability, right? So I'm going to use a bigger screen space here so we can actually see the examples, right? So let's start with utop. So we're going to define a sum function here. We're using result starting with reference 0. Then we're going to do for I is equal to 0 to array dot length m minus 1 do. I'm going to say result is equal to result plus m value in the index I. I'm closing the for loop. Then I'm returning the result. Okay, so this is written in imperative style, and we are using mutable data structures, right, in the for loop. Here no mutability is exposed. Okay, it's a fully encapsulated implementation and it is sort of safe to use. This is one preferred style of writing good functions. The other good example of good practices is application wide state. So there are some applications which will maintain state. So example is a REPL environment. So this utop is a REPL environment that we are using here, or it could be a stateful server, it could be a text editor, or it could be a cache. There are some good examples where state is maintained. So here we're going to go through a simple example of a toyline editor, which basically waits for characters on the standard input and it will exit when it reaches end of file or there's a carriage return or new line. Okay, if the character is printable, it will just print the character to the screen and it will record this in a mutable list. Okay. If the character is deleted, the stack is popped and the last printed character is erased. Okay. So we are going to use the getChar function that we defined earlier. So let's try this here. I'm going to use top find since we are going to require Unix. This is from the first part of the program, right, of the chapter. So we're going to reuse that function. So let's do getChar, let open Unix in. This is the second implementation of getChar that I'm using. Term iostc get attribute stdin in tc set attribute stdin tc sa flush. We want to set these attributes false and c echo is false, right? Then we're going to say let read the character in channel stdin in tc set attribute stdin tcsa flush term io and return the character. Right. Now let's record the character, remove the character. Let's implement these functions. Okay. So we say let record character with the state and C. We can call string dot make and append the values here. Then we are defining remove character of state. If state is empty, and return empty, else list dot tail of state. Then we define state to string state list dot state rev to sequence string dot of sequence. Okay. Now we can define the actual loop where you want to read the character. So let's do that. Let recursive loop state is equal to, let C is equal to get char in if C 004 or C is new line or C is /r, then trace exit. Okay. Then we say let yes and new state is match C with if it is 127, remove character, which is basically deleting, right? If it is the character, we record the character, state and C. Anything else, empty with state in print string s, update the state to the new state, flush std out, and we again call loop with the state. Good. So now we can actually try this. Let state is equal to reference in try loop state with exit state to string of state. So now it waits for us to input a character, right? So I can do like A, B, C, D, E, F. I can do backspace. So everything goes into the stack and gets removed from the stack. And if I hit enter, it just returns the string. Okay. So the key point here is the functions record char and remove char. Right? They don't update the state nor produce side effects. They each return a pair of values consisting of the string to print and the next state, which is the new state. Okay, that's important to note here. So the IO and state update side effects happen inside the loop function here. The state is passed as an argument to the loop function here, and the state aware code is contained in a narrow scope. So the rest of the code is purely functional. So we can actually write tests for some of these functions. So remember that the state is copied, which is generally not memory efficient. So in a memory aware implementation, state update functions would produce a a diff. Okay, it is given here. Alright, let's look at good practices of pre-computing values. So consider storing angles as fractions of a circle, right, in 8-bit unsigned integers. So character values, so this system will have 64 is 90 degrees, 128 is 180 degrees, and so on. Right, 256 is the full circle. So we are representing angles. So we can compute cosine on those values using something like let char cosine C is int of char float of int multiply that with float dot pi. We are doing decimal operation here, return cos. Okay. Now we can make this implementation faster by pre-computing all the possible values, because there are only 256 of them. So one way to do this is we say let char cos tab is array dot init of 256. Function takes argument I, call char of int, then we say char cos. Okay. This will generate all the values, the 256 entry values. Okay. Then we can define char cos C as char cos tab of int of char C. You just take the value from the array. So it is in constant time access, so it should be much faster. So for example, I can just do something like char cos of C and should return the corresponding value. So memorization technique is very similar to the previous idea. You sort of create a lookup table with previously computed values, but in memorization we actually use a cache when calling the function. So the provided arguments are found in the cache. If it is found, it is a hit, and the result is again stored and returned. If it's not found in the cache, it's a miss, and the result is computed and stored in the cache again and returned. There is a separate section of memorization, but in order to complete this section, we will continue here. So by default, OCaml programs should be written in a functional style. We want to avoid side effects wherever possible, and we want to rely on immutable data instead of mutable state. This is important. Now, a module may expose or encapsulate a state in several different ways, right? The good thing is it can expose a type that represents a state and have state creation or reset functions. Sometimes it can only expose state initialization, which implies there is only a single state. A bad practice is to have mutable state with no explicit initialization function or no name referring to the mutable state. So one good example here is the hash table module. So it has a type hash table.t. It exposes these functions clear, create, and reset, and the clear and reset functions are returning unit, which clearly signifies that there is a side effect. It performs the side effect and is updating mutable data. And so let's quickly check this hash table.t, okay, and then hash table.create. Then we have hash table.reset and the hash table.clear. Okay, so all those are defined. Now, a module may define mutable data internally impacting its behavior without exposing it in the interface. This is not advisable. Okay, you want to be very clear on the side effects. So here are some examples given here on bad practices. So let's look at this example of partition. So let partition pk array dot copy k in, let k length is rev 0 in, let m length is rev 0 in. For I is equal to 0 to array dot length k minus 1 do if pk of I then begin k dot k length, we set it to I, index increment k length, end else begin length ith index increment m length, end, close the for, we call array dot truncate, array dot truncate. Okay. Now we get error here which says unbound value array dot truncate. Now what is important for you to note is, of course, array dot truncate is not defined. So array dot truncate, for example, what it means here is if I give something like truncate 3 elements from this list 5, 6, 7, 8, 9, it will return 5, 6, 7. Right. So the input array is modified, but the function has a side effect that is not intended and not documented. Right. So we should try to not have undocumented mutation. Right. That's the issue with this example here. And if you are doing mutation, make sure you name the function correctly. Another example is undocumented side effects. So let's try this one here. Module array struct include std dot array, let copy a is equal to if array dot length a then 100,000, then analytics dot collect array dot copy a, call copy a, we end. Again here we see there's an error called unbound module analytics. Now analytics is for remote monitoring libraries. So a module called array is defined here. But this code is bad. Why is it bad? Because analytics.collect is a function that makes a network call to transmit data from a remote server. Right. So given the function a descriptive name, something like array.copy with analytics, right, and we should document the fact that there is a side effect that the caller may or may not be aware of. Right. So it's very important to make sure you properly document such side effects. And not assume that the consumer of the module or function is aware of it. Now another example is depending on the order of evaluation of execution. Let's consider this code. let id print s is print string s. Okay, and then we say let s is equal to printf dot s printf percentage s id print Monday, then we call id print Tuesday, then we call id print Wednesday. Okay. Now the evaluation order for the function arguments in OCaml is not explicitly defined, right? So the order in which the id print side effects takes place is unreliable. So in this example, the arguments are evaluated from right to left, but this could change in future compiler releases. So this also arises when applying arguments to variant constructors or when building tuples or initializing record fields. So see an example here. So we have let r is reference 0 in increment r, get the r value, decrement r, get the r value, right? So this returns 0 comma minus 1. Now the value of this expression depends on the order of the sub expression evaluation, which gets executed first. Since the order is not specified, there is no reliable way to know what this value is. So here what happens is 0. So we decrement r, which is minus 1, we read the value of r, which is minus 1. Then we increment r, it becomes 0, and we read the value 0. This evaluation here is right to left, right? But we can't assume that is the case. So it's such kind of unreliable order of execution should be avoided. It's good to be very explicit. Right? So that's the some of the bad practices that need to be avoided. So mutable state is neither good nor bad. Okay. For the cases where a mutable state enables a simpler implementation, OCaml does provide you with some solutions. So you can use references. We've seen mutable record fields, arrays, byte sequences, and imperative control flow using for and while loops. As far as possible, try to use recursion. And we have also discussed some of the recommended practices and ways to manage and handle side effects and mutable states. So with this section, we conclude the mutability and imperative control flow chapter. We'll continue looking at more of the OCaml.org documentations in the future sessions. So that let me stop the recording